Hi, welcome to video 2.6c, the last of related rates. Sorry about the recordings for the last two videos. I got rid of that background sound. Okay, so we're still in related rates. Here's number 30, air traffic control. An airplane is flying at an altitude of 5 miles, so that's the height at which he is traveling, 5 miles. Passes directly over a radar station. When the plane is 10 miles away. Now, personally, I would have thought that would have been x is 10, but they're being very clear that they're talking about the distance between the antenna and the airplane. So that s, when s is 10, that's going to be the when that we'll use later. The radar detects that the distance s, which is this distance here, is changing at the rate of 240 miles per hour. What is the speed of the plane? So here's the given rate. ds dt is 240 miles per hour. Obviously, as the plane keeps going in this direction, the distance between the plane and the radar antenna will increase, so that's positive. The speed of the plane is the absolute value of the velocity of the plane. The velocity of the plane is the horizontal distance with respect to time. So we're looking for dx dt. So we're given ds dt. We're looking for ds dt when s is 10. Here's your 5 miles, your S, your X. So I'm just going to look at this triangle right here where this would be X as well. It doesn't really matter how you look at it. Actually, I use the top triangle. So this is X, 5, and S. We need a relationship between S and X, which are these two numerator variables. And of course, the Pythagorean theorem works perfectly. We're going to take d dt of each side. We're given ds dt. We're given S, but they didn't give us x. But of course, we have the relationship between x and s. So if we replace s by 10, we find out that when s is 10, x is 5 root 3. So we replace the x by 5 root 3, isolate, simplify, and that's miles per hour. It's already positive. The speed will be the same thing. This is like number 32. Let's actually have a look at number 32. And here is number 32. Okay, number 32 goes back to number 31. So what you have is a baseball diamond. In number 32, it says, suppose the player is running from first to second base at a speed of 25 feet per second. So in my example, he's running at 28 feet per second. Mine's faster. Okay, so he is running away between first and second such that this distance x is increasing at the rate of 28 feet per second. The question is, find the rate at which the distance from home plate, so that's the distance between the player and home plate, how fast is that distance changing when the player is 20 feet from home base? Okay, so here's the distance between the player and home base. We're looking for dr dt. Now, in my case, it's when the player is 30 feet from second base. But keep in mind, if he's 30 feet from second base, and this is 90 feet, which a baseball diamond always is, then that means when x is 60 feet. We now need an equation that relates x and r only. If I pull out that triangle, again, Pythagorean theorem, you know the rest, d dt of each side. They said when x is 60, here when you take the derivative, you'll have 2r dr dt. You'll need to find out what r is when x is 60 by plugging it back in. Number 34a, it says repeat number 33. Here's number 33. You have a man 6 feet tall who's walking at a rate of 5 feet per second toward a light. Notice that in number 33, he is walking away from the light. Okay, so in our case, he's walking towards the light, which is the distance between him and the light. Obviously, that distance is getting smaller and smaller. So in number 32, he's walking at a rate of 5 feet per second towards the light. That means dx dt is negative 5 because that distance is getting smaller feet per second. Then in number 34, it tells you that the light is 20 feet above the ground. So that's how tall the light is. And we're repeating the questions for number 33, which is at what rate is the tip of his shadow moving and at what rate is the length of his shadow changing. Okay, so if this is the light source, then the shadow will be behind him. There's the feet of his shadow and the head of his shadow. So this is the length of his shadow, which is part B. But the question for A is at what rate is the tip of the shadow moving? So what's going to happen is the tip of his shadow here, how far is it away from the light? And that is the y that we're looking for. So we're looking for dy dt. Now notice there's no when, and the reason is because we won't need one. Okay, so we have, this is 20 if I pull it out and just have it geometrically. There's the 20-foot tall lamppost. There's the 6-foot tall man. X is the distance between the man and the light. Y is the length of the tip of the shadow, but the distance between the tip of the shadow and the light source. Again, we have similar triangles by AA, 20 over 6 equals y over y minus x. Make sure you take sides of the triangles. Notice x is not the side of a triangle. So if I take the vertical side of the large triangle over the vertical side of the small triangle, I then need the horizontal side of the large triangle over the horizontal side of the small triangle. Do a cross product, it'll just make life easier, simplify, and that's a much easier thing to differentiate than this quotient rule over here. Okay, we're now going to take d dt of each side. And as you realize, they gave us dx dt and they asked us to find dy dt. It doesn't matter at what point in time he is away from the light. This is going to be a constant rate of change. And we end up with negative 50 over 7 feet per second. Part B, what rate is the length of the shadow changing? Now I'm going to call that length z. Calling it y minus x will just cause havoc. So I'm given, again, still have the dx dt is negative 5 feet per second. How big, what is the rate of change of dz dt? Now, whether it's 10 feet away doesn't really matter. Because it's going to set up the same thing. This time it's going to be 20 over 6 equals x plus z over z. And then you'll do the same thing, cross product, simplify, take d dt of each side. Number 42, angle of elevation. A balloon rises at a rate of 4 meters per second from a point on the ground 50 meters from an observer. So here's our paraplegic. He's lying on the ground. Take 50 feet away. From there, the balloon is rising at the rate of 4 meters per second. So dx dt equals 4 meters per second. Find the rate of change of the angle of elevation of the balloon from the observer. So from the eyeball of the observer to the balloon, that's one side of your angle of elevation. The other side is always a horizontal coming out of the eyeball. This is to just show you always that one side of an angle of elevation or depression is horizontal coming from the eyeball. The other side of the angle is joining the eyeball to what the eyeball is looking at. So we're looking for d theta dt, specifically when the balloon is 50 meters above the ground, which is when x is 50. We need an equation that relates x and theta, and this time we're going to need trig because we've got an angle here. So that relationship is going to be that the tan of theta is x over 50. We're going to take d dt of each side. We're going to get secant squared theta d theta dt equals 1/50th dx dt. We'll replace dx dt by 4. Now, but then it gave us when x is 50, and there's no x here for us to replace by 50. But there is a secant squared theta. If you go back to your diagram, replace the x by 50. We already know that this horizontal distance is 50. Obviously, if both these sides are congruent, it's an isosceles right triangle, and that angle is 45 degrees or pi over 4. Therefore, the secant of pi over 4 will be root 2 over 50 root 2 over 50, or just root 2 over 1. We're going to square that to get 2. This becomes 2/25. Isolate your d theta dt, you get 1/25. Theta is an angle, it's in radians, and the time was given to us in seconds. Okay, I think there's one question in the textbook, and I think it's an even question, I'm not sure. But they don't have a lot where they give you 2 rates of change and ask you for a third one. So here's an example. 2 straight roads intersect at right angles. Car A is on one road moving toward the intersection at a speed of 50 miles per hour. So that's one rate of change. Car B is on the other road moving away from the intersection at the speed of 30 miles per hour. So that's a second given rate of change. When car A is 2 miles from the intersection, in other words, when x is 2, and car B is 4 miles from the intersection, in other words, when y is 4, how fast is the distance between the cars changing? Well, the distance between the cars is z, so the question is to find dz dt. So we're given dx dt. Now remember, car A is moving towards the intersection, so x is getting smaller, so that's why it's negative 50 miles an hour. But dy dt is positive 30 miles an hour because car B is moving away from the intersection, so y is getting bigger. The question is to find dz dt when x is 2 and y is 4. So for the first time, we need an equation that relates all three variables. Obviously, that's the Pythagorean theorem. Take d dt of each side. They gave us x, they gave us dx dt, they gave us y, they gave us dy dt. We're looking for dz dt. The only thing they didn't give us was z, but of course we have that equation, and we know that we're talking about what happens when x is 2 and y is 4. You'll solve to find out that z is root 20. And there's your dz dt, and of course it's a length which was in miles, and the time was in hours in this question. And that's the end of video 2.6c.